All right, I think that's it. I'm gonna be moving around today, so I don't know if I'll be super audible. So, but I'll keep it going here. All right, guys, here we go. I want to talk to you about just kind of finishing yesterday, and then we have a couple things to talk about in the lab and kind of a little bit of scheduling stuff. If you haven't noticed yet already, I put all of you guys on the Physics Club Google Classroom, so just hit accept on that. If you're coming to the meeting later, again, it's going to be about 10 minutes after school. I try to knock it out super quick. Basically, the main thing I'm going to be doing is kind of going over that write up and like highlighting spots where students in the past have not paid close enough attention as they need to. Because in one of these projects, you're basically expected to kind of cover particular criteria, and if you do it, great, credit, you're awesome. Okay? And then, of course, you can go to the next level and kind of compete in that if you so choose. But yeah, you at least have to hit that. And I'd hate for you to do a bunch of work and not get credit. So please make sure that if you can't make the meeting, which is fine, that you pay very close attention to reading that carefully on exactly what you need to do. For instance, the supports are going to be sitting a certain distance apart. I can't remember what it is. I just looked at the write up and I can't remember. But one year, I think they were 7 inches apart, and somebody made a bridge that was 6 inches long. And then they looked at me and said, "What are we going to do?" And I said, "I don't know. Bridges don't work like that. You can't make a bridge smaller than the gap it's supposed to expand. Can I get credit? Would you want to drive over this bridge? No? So no. So I don't want you to do a bunch of work and then not get credit for that. Hold on just a second. Just making sure everything's on the up and up. Cool. All right. When we ended yesterday, these were the points up on the board. Actually, I will write them over here that I stole off of that. Obviously, I didn't do it again because I want to take all that time to do that. 173 Kelvin. I know this is a repeat, so I want to go really fast here. 0.0 kilopascal, 0.0 kilopascal was 1 point, and then the other point, I believe, correct me if I'm wrong, was 423 Kelvin. And I said 83.0 kilopascals. But as you hopefully learned yesterday, your graph might be slightly adjusted to my graph, which might mean that you actually probably should get different results. As a heads up, obviously, if you get a different result from somebody else, that's completely okay, as long as it's around that particular range. That is, as we stressed, I think I stressed this yesterday, I can't remember. That's one of the main reasons why your graph needs to be a half a page, because technically you're freehanding in there. Technically it's not perfect, but the bigger it is, the more accurate your graph is going to be. To put this in perspective, on the AP test, they expect you to do this. They expect you to see data that's not correct, go through the middle, and as you grade the AP test, if you look at the answer key, it says this is the range that we expect it to be in. This is a reasonable range for somebody that is legit trying. So to understand that is something, a practice that is prevalent, not just kind of in here. We're not just winging it. Obviously, slope we talked about real quick. So there it was. Change in y over change in x was 83.0 kilopascals minus 36.0 kilopascals. Spainhour, you don't have to write the 0.0. Yes, I do. 423 Kelvin minus 173 Kelvin. And if I'm not mistaken, that ended up for me yesterday as 0. I want to say 118, but 18? Just go ahead and grab the calculator real quick. And we have 83 minus 36 divided by the quantity of 423 minus 173. Notice once again, units up there, 0.188 kilopascals per Kelvin. Because that's what slope is. Slope is the general ratio. What does that sentence say? What does that number mean? That number means if I increase by 1 degree Kelvin, on average, my pressure should increase by 0.188 kilopascals, or 188 pascals. Now, this is, I believe, roughly where we ended off yesterday, and then I asked you for the slope general equation. Now, when you find the equation of data,
let's even kind of shift away from equation of the line. Yes, it's equation of the line. This is the relationship of the data. What's very important in this transitional spot is I bet you are very, very good at the mechanics of doing this. But I also want you to have a more deep understanding of what the heck it even means. To that end, like I said a second ago, what does this number mean? Well, if I increase at a steady rate, 1 degree Kelvin equals 0.188 kilopascals. Over here, try again. Over here. Now, what is this? This is the generic form of the line, okay, which is great. And you've used it a crap ton. Usually use M instead of K, but 6 of one, half a dozen of the other. That is not super useful for us in science because it doesn't mean anything yet. So we are going to, in turn, replace every single part of that with something specific to the lab, okay? Now, the first thing, of course, that we did is we found this constant. The second thing that, of course, we do is we find this other constant over here. And as I said yesterday, you will not just assume what it is, you will calculate what it is. Of course, you can calculate what it is by taking a single data point and plugging those in to their respective spots. So here I have 83.0 kilopascals equals 0.188 kilopascals per Kelvin multiplied by 423 Kelvin. One nice thing about units right now is you'll notice that if I cancel them appropriately, I should be left with the correct units plus B, and I'm solving for B, or the y-intercept in this case. So I multiply that over there on the right side, 0.188 times 423, and I get 79.5. Again, this is one of those spots where you could write it as another step, or if you understand what's going on, please understand that you don't divide underneath, but of course you subtract on the other side because it's adding over there. So I have 83 minus that. If you just showed this work and then immediately had the y-intercept is 3.476, or actually let's just go ahead and round to 3.48, that's fine. What should the units be on the y-intercept? Kilopascals. You can see this because A, it's just the Y value, but also if you follow the units here, which we'll talk a little bit more about tomorrow, kilopascals plus kilopascals is in fact kilopascals. All right. The last piece of this, which is super simple, I told you that we are going to replace every single piece of that. So we've replaced both the constants, the K value and the B value. What do you mean by replacing the Y and the X? I want to be very clear in here right now when I say this, because it seems like a hard-fought battle for me at the beginning of every single year with students. We will not use Y and X for a final answer ever unless we are measuring yotas and xylophones. Okay? The variables that we will use will pertain particularly to the question at hand. So, in other words, if I was graphing displacement, this is going to be a little bit weird, if I was graphing displacement in the y is now delta x. Now, I would still write this if I were you, just to give you a generic thing, but basically your final answer should have the correct constants with units, as well as instead of your y and your x, they should have the actual variables measured. Now, early in the year, when you don't know what they are, just go ahead and use the first letter unless you're pretty sure otherwise, and we can talk about what that is. In other words, what were we graphing on the y yesterday? Pressure. So not the unit, but instead of y, I'm going to write pressure is equal to K, which is 0.188 kilopascals per Kelvin, times, what did we graph on the x? Temperature, so capital T, plus 3.48 kilopascals. Now, a couple things to note, especially as you guys go into this, and I saw Courtney's work earlier, which I'll look at. Sorry, I should have warned you I was going to probably use your reference. But understand this, okay? These pressures these pressures are extending from like obviously 0 to all the way up to, we got up to 83. Okay, so let's say we were expecting on this lab, let's say we were expecting something that looks like this. We were expecting it to go through 0, 0. Okay, obviously it doesn't go through 0, 0. But is 3.48 pretty darn close to 0, 0 when you take it on the scale from 0 to 83 or 86? I would say yeah. I mean, it's within about 4%. 4 to 5% seems very reasonable as a result. So am I going to ever get perfectly 0? No, this is not perfect data. To that point, is it very possible that I calculate a negative answer here? Yeah, 100%. Shift this just slightly, adjust it a little bit upwards. Like this. Okay? I know I'm being drastic here, but is it very possible to get a negative answer? Sure. If I got, say, in this particular case, a negative y-intercept of, say, negative 2.3 kilopascals, obviously it feels a little bit weird to get a negative value, but keep in mind why you got that negative value. You're not saying that it's actually a negative answer at 0. This is just part of the error of your lab that got adjusted a little bit. And is negative 2.3 kilopascals any worse than positive 2.3 kilopascals when you're looking to get an answer of 0? No, it means pretty much the same thing. We were expecting. Now, if you were expecting to get 40 and you got 0, now we have an issue. Now we have a serious issue that we need to certainly consider. But we will talk about that. Any questions as to, I think if you did the work last night, which I appreciate you guys working ahead, the only thing that should probably change is I would imagine you're using your y and your x's, and you just need to shift those over to the other letters instead, and that's literally it. The other big mistake that people make though here, oh, that's interesting. I didn't do that on purpose. Oh well. Anyway, the other big mistake is always what I said, numbers have units. Your constants should always have the correct units. Questions on that? Okay, so this is a really good transition actually into today's conversation, kind of as we end yesterday's conversation. And we are going to talk today, I don't even know how I turned that on to turn it off. I figured it out. All right, it wasn't that hard. So we're going to talk today about your data analysis and error analysis. And I have an entire day scheduled for this for 2 reasons. One, there's a good amount of conversation here to be had about what's going on in a lab and that type of thing, sure, but I also want to give you a little bit of space to kind of talk to people and brainstorm on this and not just be kind of left to your own devices in order to figure it out. Now, let's begin with the data analysis because it fits perfectly with the end of the last conversation. So when you do a data analysis, well, let me back up. I'll remind you what I said the other day, and that is, when we do a lab, you can kind of take it like this right now. Spanauer said such and such is the case. I don't believe him. Labs are meant to basically be your real connection to life and have life tell you, have the world tell you what is actually the case mathematically. Does this match with what we expect it to be mathematically? Okay? So right now, we only have one equation that we are looking at. We are looking at this equation right here. A couple things to point out. You will notice that I did not put I don't know if I talked about this the other day. My apologies. Did I talk about the fact that that is the symbol for average velocity? Okay, good. All right, so you might notice then that I did not make that average velocity, but instead made it constant. And we talked about the fact that they're the same equation and the y of the same equation. Why do I have a constant velocity up here for the lab the other day instead of an average? Discuss quickly in your group. The question on the table is, why did I put a constant velocity up here for your lab the other day? Think about your lab the other day as opposed to an average. Or, if you're struggling with that, what's the difference between a constant velocity and an average velocity? Discuss. Thoughts? Any questions? Answers? Concerns? Sometimes when we do something like this, please understand this is a conversation. I don't expect you. Sometimes I don't know. Sometimes I don't know what you know, and it's important to be like, yeah, I just tell me you don't know, which is fine. Then I know I need to kind of go back and cover that again. So, what do we know? No idea? Any idea? Okay. So we discussed the other day is I commented on the fact that if we were to take the average velocity the average height of people in here, you would add them all up and divide by the number. Yes? Okay. Why would the average be different from every person? So when would we consider you guys, probably not likely to have a constant height? Correct. So, what's the difference between average velocity then and constant velocity, and when are they the same?
You use constant velocity in real life because we're constant velocity.
Well, you would look at the situation. What was true of the car? The car was constant. Since it was constant, if we were all the same height, would that constant number and the average be the exact same thing? Boom. Since the velocity is constant, that is the average. When will constant velocity then not match the average? When we are changing our velocity, which will happen on Thursday. Okay? So that'll become certainly important for that. But this is our equation for constant velocity. It means something very simple. You can see it numerically if I just do this. I should be able to ask all of you, hey, firstly, you should be able to spot that this is in fact a velocity, simple by its units. Okay? And as it's a velocity, technically in your head you can go, technically there's two numbers there. There's 8 meters on top and 1 second on bottom. And I should be able to say, hey, what the heck does that mean to a person, to a thing? If something is going 8 meters per second, what is happening? That's all I need. Yes. And it's literally as simple as that, and that seems kind of overly simple, but trust me, Thursday's coming. All right? So yes, in the time of 1 second, 8 meters progress. Okay? But we didn't measure displacement the other day, did we? Okay? In a lab, what you do is you measure two things. You have two variables. Okay? Some science classes say one variable, but really it's you change one, you measure the other. There are two things changing. There are two variables. What do you do with everything else? In a lab, what do you do with absolutely everything else? Keep it constant. So it does not affect the relationship whatsoever. So what we then do is we look for a relationship similar to this one that has the two things that we are changing and try to hold everything else constant. So what two things did we change in the lab? Or did we left change in the lab? Close, but not quite. Close, but not quite. Position. It was weird. I forced in a weird spot, but I said we're going to change position. Now, is position currently up on that equation? Yes and no. No, it's not, but is it actually buried inside that equation? Yes. Where is position buried inside of? The displacement. Right. So, we can, how do you get the change in anything? There. Now, as you look at that equation, are there two things up there that we're changing, and are there two constants? What are the two things? Well, discuss quickly in your group. Out of those 4 variables that are now up there, what are the two that are changing, and what are the two constants? I'll give you 30 seconds to a minute. It shouldn't take long. All right, what do you got? What two changed? Yep. Time interval and position final. And therefore, this should be easy, but what two do we keep constant? Velocity, simple by the nature of the car itself. And you guys pretty much all know what your position initial is. Yes, not the same to everybody else, but you have an initial position, right? So that means even though, and this is going to be a weird thing to get used to, even though there are 4 variables up there, there are 2 variables up there. Does you understand that sentence? Even though you see 4 variables in terms of math, are all 4 of them allowed to change? No, there are only 2 of them that are allowed to change. So watch this. What I'm going to do, and I'll explain why in a minute, and you'll have more background to do this yourself in the futures. I'm going to do a little bit of algebra and isolate the position final. Actually, you guys should be fine on that. Take 30 seconds to a minute with just the variables and isolate position final on one side of the equal sign. Should be, like I said, 30 seconds to a minute. I know this is super easy, but humor me. Let's make sure we're all on the same page. Take that equation right there and isolate position final on one side and everything else on the other, following basic algebraic rules. To encourage this, I'm not going to go over it unless you need me to. Just going to list the final answer. Use delta t. Carry the deltas around. They're important. $15 more seconds. All right, you should have gotten this. Position final is equal to velocity times time plus position initial. Obviously, the order could be different. You could isolate it differently. Also, quick heads up, because I know math usually likes the position final on the right side. As I'm doing this algebraically, so I don't mix stuff around, probably what I'm going to actually end up with is this. Completely fine. Maybe it makes you uncomfortable or whatever because you're not used to it, but no problem with that whatsoever. We say isolated on one side. There it is. Now, what shape, when graphing your information, did it make? What shape did your graph make? Not all of you might have done it yet, but hopefully at least a handful of you, yes. A linear function. What is the equation of every single linear function? Correct. Now we understand certain things about that equation and what they particularly represent. Okay, what is the slope? The slope is the change in the x variable. Okay, how the x variable affects the change in the y variable. What is the y-intercept? Well, the y-intercept is whatever the heck the y is when the x is 0. So what you can now do for data analysis is you can then start to predict 3 things that are going to become particularly important. In your data analysis, you will then basically write/use equations to show the reader, not me, this fact. What does your data essentially mean? What have you isolated? And there's 3 things to discuss mostly. Number 1, what do you expect the shape of the graph to be? 2, what do you expect the k constant to be? Notice I did not say slope. We'll discuss why, probably in about a week's time. And 3, what should your b constant, this one will, at least in this class, always be y-intercept. And when I say what should they be, I'm not meaning numerically. I'm meaning like conceptually. Like, what does it represent? Okay, you've got these numbers. What the heck do these numbers actually mean? So, as of yesterday and today, we talked about finding the equation of the line. So what you should hopefully get done pretty quick is you have your data. When you do your data in your lab notebook, again, lab notebooks, write it nice. Like, if you haven't yet already, please make sure it's presentable, like it's very obvious. Like, don't just have it scratched. Like, if I were you doing the labs, usually I would, like, because I have terrible handwriting, I would usually like scratch the information, the data on like a separate sheet because I know I'm going to be like all over the place. And then when I'm going into my lab notebook, I'd make it look nice. I'd make sure the units are really well known, that type of thing. Okay, easy peasy. Second step, of course, is to do the equation. To do the graph to represent what it is. The next is to find the equation of that particular relationship. In this case, a line, which we talked about yesterday, and we talked about a little bit today. Next step is the data analysis. So when you get to the data analysis, you have the equation of your line. A couple of heads ups here. Actually, no, we'll go over it now. Now, if you look at these two things in comparison with each other, you can start to glean particular information. For example, what did we put on our y-axis? If you graphed it, what did you put on the y-axis? Position. So this is your y, right? What did we put on the x-axis? Time. Boom. There is your x-axis. Now, if you start to compare these two equations, what the heck does that mean your slope actually represents? The velocity. The velocity of the car itself. You can now tell what the velocity is. Now, here's a really good point that students make, not out of being laziness, but out of complete seriousness. They go, great, Spainhour, we found velocity. Why the heck did you spend 2 days talking about this and a day to get the data? I could have found the velocity really easy. All I needed to do was get one displacement and one time. That's it. Give me a displacement, give me a time, boom, I've got your velocity. Why the heck did you need me to go through this lab? And the answer to that question is kind of answered in the next part, but I'll say it right now. It is this. We know there is error. We know there is missteps for whatever reason in measurements, even if you do it perfectly. So, when you look at a graph that might have a bit of error, it's probably ish what yours is going to look like, I'm guessing, okay? What you'll notice is that more data means the actual answer trends towards accurate. These dots on the top part of the line will tell you that the object is moving slower than it actually is. These dots on the bottom of the line tell you it's moving faster than it actually is. So that means if you were to grab any of the dots on my fake graph I just made, they would 100% be wrong. By taking more and more and more data, if we had all the time in the world, I'd make you take 20, 30 points of data, okay? We make it more and more accurate. That's why we came back and did our second line of data if we could. For some of you guys, that means it's going to be looking a little bit more like this. More data means the actual answer trends towards the 100% accurate answer as opposed to having to deal with error. Does that make sense? Okay, so what does your data analysis look like? Well, for starters, heads up, there is kind of some stuff that I've put online so you can kind of look through and see like some general things about this. But for right now, the main thing that you want to talk about is this. One, what should the shape be? Not what it is. You know it's linear. What should it be? And the answer is should be linear. Why should it be linear? Well, we talked about this the other day when talking about generic equations. What makes this different than a parabola, different than a hyperbolic, different than a square root? What specifically where? Correct. Once your y is to the first, and that's important, once your y is to the first, the x power will tell you exactly what it needs to be. Look over here. Is our y, air quotes for people listening, is our y to the first power? Yes. Is our delta t to the first power? Then it needs to make a straight line if that is in fact the equation. When those are to the same power in the equation, even actually before you did the graph, we should have been able to predict that this was going to make a straight line because this is to the first power, your y is to the first power, and your x is to the first power. Does that make sense? Next, k constant, or in this case, slope. How can I tell what the slope is? Well, just look real quick. Where do we find the slope? If we put it in this format, the k value, or the slope, is multiplied next to the independent variable. So what is our slope here? Our slope is velocity. And finally, the b value, the y-intercept. Mathematically, understand, real quick, what is the y-intercept? It's whatever the heck that is when that's 0. Okay? You probably knew that mechanically. Let's talk about this conceptually. What does that mean? That means, what is the position when time is 0? And hopefully, as I said that sentence, conceptually you go, oh, that makes perfect sense. My y-intercept better be the initial position. Does that make sense? Or if you want it more, kind of mathematically, the k value is multiplied next to the independent right here. The y-intercept is added next to that particular value. Also notice that again, of these 4, these two are variables. These, even though they look like variables, are actually constants in our lab. Questions, concerns about this? Okay, so you're going to be asked to essentially write a paragraph to the reader, essentially doing what I just did for you. Okay, I know it's not going to be perfect to begin with. We're going to work on this throughout the year. You're going to do this quite a few times throughout the year. The main things, again, to focus on when doing that is tell the reader why it should be the shape it is, not what shape it is, why it should be the shape it is. What is your k constant? What does that mean? One thing that will help you with that, by the way, units. What should the units of our slope be? Centimeters per second. Kind of makes sense then that the k value is our velocity. And finally, what is our y-intercept? We'll talk a little bit more about this moving forward and add a few pieces, but are there any quick questions right now? All right, let's move on to error analysis. Error analysis is going to go a little bit quicker, but also arguably be a little bit more vague, okay? And if you just avoid a couple of pitfalls and try pretty decently on error analysis, I will work with you. I'm going to pretty much just give you the points and just say, okay, as long as I can tell they're kind of trying to make this better, better, I'm probably not going to count off like you didn't do this, you didn't do this, you didn't do this. Okay, number 1, error analysis is a conversation with the reader in which you discuss potential types of error and how much they maybe should affect your overall results. Okay, first things first, I said this the other day, error are reasons in a lab that the data is not perfect, that is not human mistakes. So a handful of spots that will not be on this conversation, okay? We screwed up and moved the, and we screwed up specifically and read the wrong number. On the opposite side of things that will be on there, human reaction time. Human reaction time is unavoidable. Unless any of you in here are robots, you will have human reaction time. That is not considered a mistake. That's part of that. Okay? Now, reading the wrong number is definitely not going to be on there. But some of your guys chose a technique where you slid the meter stick. Not getting mad at you, 100% understand why you did it, but you can see where that technique potentially could present particular pieces of error into your overall answer. That can be part of your conversation. Okay? So never. Oh, and when we talk about error, we are not talking about the creation of the graph. Once again, there's certain pieces of things that are just understood. Like when you draw your line of best fit, obviously it's understood that there was human error. You hand drew that. That doesn't need to be part of it. Another thing that does not need to be part of it is the level of accuracy of the particular thing you're using. Like the fact that a meter stick can go down to a millimeter but can't go further. The reason why that is let me ask you, okay? Did the millimeter probably matter that much to the accuracy of your measurement? No. Honestly, if you dropped the millimeter off the table, you probably were just about as accurate. Meaning, if you're like, well, we didn't measure the the tens of thousands of place or the hundreds of thousands. Yeah, sure, you could be more precise, but is that going to help you? All right, so I've talked about what it isn't. I want to give you at least about 5 minutes to brainstorm in your group then, what could certain sources of error be? So you will not talk to the reader about mistakes, but when you think of the lab, what were some things that we did, the ways that we did things that potentially caused the data to not be perfect? 5 minutes time, discuss real quick. We'll meet back here at the end, talk about it, and then we'll get you out of here. Obviously. But discuss real quick, about 5 minutes. Does anybody know what lore is? Is he okay? Probably the hardest part of this is that I think when you've done previous labs, you're on your calculator, like, oh, I should be able to knock it out like in 2 seconds. You kind of got to think a lot of times in depth about this and be sitting there and like, okay, why would, like the hardest part of error analysis for some of you is not the writing of the error analysis, but probably this step, the brainstorm ahead of time of everything that could go in the error analysis. I got about 5 or 6 right now in my head. Does everybody have a lab notebook? She asked me to record. That's why it's up. By the way, that also brings me to an excellent point. If any of you guys can't make it on a particular day and really would like me to, sometimes I'll push back if it's not the right day for it, but I'm happy to record the thing and post it and send it out. So. And sometimes you're specifically going to skip school just to miss this class, so don't worry about it then, honestly. That's not true. I've had a lot of students in the past. I think the biggest point of pride, and it probably shouldn't be, this is nerdy and ridiculous. The biggest point of pride is like, usually like when students like leave to like go do blood drive and stuff, they're like, well, obviously I'm not gonna miss physics. I'll go to physics and then I'll miss the rest of the day. All right, so let's go. What do you got? I'm just gonna put it up on the board. What do you got? Here. So I'm gonna put that under human reaction time, but 100%. Okay, and you're going to discuss that a little bit along there. Like, obviously, you're not just going to put this in a list. Like, it's going to be a conversation with the reader, so there shouldn't be a paragraph. But yeah, I would say human reaction time. Jack. 100%. 100% human reaction time. Car drifting. I'm putting it up here to help you out on this one, guys. But again, when you write this, it'll be a paragraph to specifically. What else you got? What's that? So I'm gonna put that on up here. I'm gonna put that alongside of probably what goes with it. If nobody has it, I'll. What you got?
I was gonna say when we lifted up the car, put it back down.
So yeah, okay. So just simply placement of car. So I'm gonna go back to that one real quick, and then I'll hit this one as well. So stuff on the floor or this, just your wheel slipping. right? If there was a little bit of dust on the wheels and it slipped, then it wasn't traveling distance than it should be. Okay, so debris. I can never spell debris. I think this is right. Debris. That's not right.
No, E.
I don't care. It's fine. You've got the general gist. All right. Debris spelling error. All right. A debris or wheel slip, I guess. I don't know. And then, remind me, Shauna, you said
When we
pick up the car, yeah. For a handful of you, I said it already, but I mean, obviously, I only gave you two, so you were gonna have to slide it one way or the other. But obviously, like if you chose to do it kind of in real time, that meant you had to go a little bit quicker, which probably meant you slipped a little bit more. I'm trying to think of other ones. Here's one. If the batteries were fading out in your vehicle, it could have changed the velocity. Now, whether or not you put that one in there should be up to whether or not you noticed anything significant. Okay? If you noticed anything significant in your car, I might add that. Don't just add it to add it. Like, don't just put it like, if you're pretty sure your car was constant the whole time, there's no reason to add that up there. Let's see. Again, the big thing that I don't want to see is human mistakes or any description of human mistakes whatsoever on that error analysis. So what I'm thinking right now is like the first paragraph should kind of be this like spot where you're just kind of talking about this could happen, this could happen, this could happen, this could happen. Okay. The second paragraph that you have and kind of the end paragraph should be a discussion of, okay, do I think this significantly impacted my results and therefore you probably shouldn't trust it? Well, let's just look at the graph as a physical representation for that, right? If I have data points that are like this, even if I got what I expected, okay, even if I got under data analysis said I was expecting this, I got this is exactly what I wanted, awesome on data analysis. At the end of error analysis, I would probably point out, holy crap, look at the spread on that data. The physical representation of error on a graph is the space between the line and that particular point. If they are particularly spread out, I know you guys have heard this before in science, okay? You got a target, boom, accurate, right? Precise. You good with that? So here, I would argue that this set of data is accurate because it's what we got, but it's not precise, which means I pretty much probably just got lucky and you shouldn't trust it. For the most part in here, we'll talk about it from lab to lab, you should, in that second paragraph, mostly say, yeah, we had these errors, but I don't think it affected it in a significant way. If you do think there's one of them, I'm just going to kind of use, like if I was making you go in depth, I'd probably have you go like error by error and be like, no, I don't think this affected it. Yes, I think this affected it. But let's just do a catch-all. No, I don't think any of them did. Or yes, but take the time to think about it. Like for example, human reaction time is 0.15 seconds. If your car is going 30 centimeters per second or whatever it is, 0.15 seconds, okay, is about 4 to 5 centimeters. Does 4 to 5 centimeters too fast or too slow really going to change your overall results here? No, probably not. Picking it up, does that cause error? 100% it does. It should be up here. But do I think that that affected things by more than a centimeter? No, probably not. The wheel slipping. Yeah, it technically should have gone a different distance because of the slipping and potentially the drifting. But again, it's like that conversation. And ultimately, my guess is that you should end up with, no, I don't think it affected very much. When I look at your data analysis and error analysis, this is kind of a teachery thing, but also like, spend the time and effort here, guys. Honestly, if I look at somebody and they've got like I don't want to tell you like how long it needs to be, but roughly speaking, I'm thinking a good one for a simple lab is probably like half a page if you're like doing it right and discussing things with the reader for both of them. You might go longer than that to do it well. Just know this, okay? If I see this on an error analysis, this is what's going to probably irritate me the most. Error analysis.
We dealt with human reaction time, card drifting, and debris.
Read that from the perspective of a reader who had no idea what you were trying to write. Okay, that's unhelpful. I don't understand why that's there. Think, empathize with your reader. Okay, you are in a conversation with your reader. Discuss it with them. Okay, they should know why you have an error analysis. You don't need to explain what an error analysis is, what a data analysis is. Okay, you can just do it, but make sure you're talking to them. And again, I'm going to work with you. If I see you putting in the effort, I'm going to make sure you're good here. Any questions about what it is we're looking for, what it is you need to do? You should have everything you need now to finish the first lab. Yes? Yes.
Oh, do we type or write this?
Write this. It should all be, ideally, it should be in that notebook. Okay? That should be kind of your final results. Right there. Any other questions? This is due, I believe, on Thursday. Heads up, I put another assignment up, intro skills, this morning. I made some space in the calendar, but that's not reflected yet on the calendar, so I don't want you to think, like, don't freak out about that, don't start it. We're going to talk about that a little bit tomorrow, and I've already made space in there for you guys to be able to tackle some of that stuff. I wasn't going to tackle it at all, and then I noticed I think there are at least 2 skills that, yes, you should be able to do, but I don't think you have any background in whatsoever, so I need to talk about them very, very quickly tomorrow. Any other questions about what your lab report needs to look like? Fair enough. I'm done.
Bye, Lillian.